Mathematical thinking in science. Here's an example from Daniel Kahneman's best-selling book, Thinking, Fast and Slow. Steve is very shy and withdrawn, invariably helpful, but with little interest in people or in the world of reality. A meek and tidy soul, he has a need for order and structure, and a passion for detail. Is Steve more likely to be a librarian or a farmer? There are two broad groups of responses to this question based on the analytical technique people used. In one group, people examined qualitative attributes such as personalities and characteristics of jobs. For example, they may say, Steve is more likely to be a librarian because he likes to organize things. Or Steve may be a farmer because he likes helping people. In the other group, people reason quantitatively. In Kahneman's book, a statistician explains, there are more than 20 male farmers for each male librarian in the United States. Because there are so many more farmers, it is almost certain that more meek and tidy souls will be found on tractors than at library information desks. As we can see, this statistician explains the relationship between two measurable variables, the number of male farmers and the number of male librarians. The contrast between the qualitative analysis and the quantitative analysis indicates two important components in mathematical thinking: measurability and relational complexity. More details about these two components can be found in several articles by Patrick Thompson at Arizona State University. Measurability refers to that a variable can be measured and presented in terms of numerical values, even you do not measure it. Relational complexity refers to the mathematical and quantitative relationships among the variables. In the example above, the statistician made the inference about Steve's profession based on the quantitative relationships between two measurable variables. What is mathematical thinking in science? In science, the mathematical relationships among measurable variables are conceptualized using scientific ideas. For instance, we explored student understanding about extensive and intensive quantities in science. Extensive quantities are properties of a system that vary with its size or amount of material, while intensive quantities remain constant regardless of the system's size or amount. For example, mass and volume are extensive properties dependent on the amount of material in an object, while density is an intensive property that remains constant regardless of the amount of material in the object. This mathematical relationship has a scientific meaning. Mass and volume are properties of objects, while density is a property of materials. Mass and volume are properties of golden bars, coins and crowns, and density is the property of gold. In a mathematical thinking in science project, we created assessment items to diagnose high school students' intuitive ideas about thermal energy and temperature. Thermal energy is an extensive quantity, whereas temperature is an intensive quantity. Here is one item. The item asks students to compare the cold water in a bathtub and the hot water in a teacup. Which one has more energy? Which one has a higher temperature? After a student completed the assessment, the researcher interviewed him. Here is their conversation.
Which one do you think has more thermal energy?
I would say the water in the cup, not the bathtub.
Well, what are you thinking?
Depending on the size of the containers, if you have something really large size, only 1 degree less, that will obviously have more energy in it related to heat.
The student initially provided an incorrect answer to a question that used the term thermal energy. Later, the student explained the phenomenon in his own words. He used something really large size to refer to the amount of water, used 1 degree less to refer to temperature, and used more energy in it related to heat to describe thermal energy. His explanation implies a scientific reasoning, which recognizes that the thermal energy of water is an extensive quantity that depends on both the amount and temperature, but temperature is an intensive quantity. Despite not using normative scientific language, the student did use scientific reasoning to analyze the phenomenon. The interview data indicates that the item is not effective in diagnosing students' reasoning. Therefore, the researcher revised the item. This is the revised version. It does not use the term thermal energy. Instead, it asks students to explain two phenomena. The hot water is more likely to burn someone, while the cold water is more likely to melt an ice cube. While temperature explains the first phenomenon, thermal energy explains the second phenomenon. Let's look at students' responses to this revised item.
Hugo, the hot water will make the ice cube turn into steam rather than melt.
Sarah, the ice cube will be more used to the colder water than the hot water, making it melt 100%.
Hugo describes an observation. Sarah uses human analogy to construct the explanation. Neither of them analyze the phenomenon.
Tom, the water is warmer than the ice cube and the heat will go into it, melting it, and hot water burns because it is hot.
Tom provides a qualitative analysis that focuses on one attribute, the hotness of the water. He does not identify any measurable variable or quantity.
Jean, the temperature of the colder water in the tub is higher than the freezing point of water, explaining why the ice cube melts. The hot water is nearly triple the temperature of a person, causing the skin to burn.
Jean demonstrated an understanding of measurability by reasoning about the numerical differences between the two temperatures. However, she did not recognize the distinction between energy and temperature, indicating that she did not understand relational complexity.
Lily, in the teacup, although much hotter, has much less water in the cup. Once an ice cube is placed, it will rip through much of it while rapidly bringing the temperature of the teacup water down to a point where the water has much less energy to completely melt it. Therefore, the hot water won't completely melt the large ice cube. In the bathtub, although much cooler, has much more water at a constant temperature that can melt ice. One ice cube won't dramatically affect the bathtub's overall temperature, while one ice cube will dramatically affect the teacup's temperature.
Lily not only distinguishes between temperature from energy, but also explains the relationships between these two quantities in the phenomenon of melting the ice cube. He provided a scientific explanation.